Alright, next section is when we try to evaluate the efficiency of such system, CHP system. How do we calculate their efficiency? Okay, it's that section. So let's look at a simple Rankine cycle. If I ask you, here is a simple Rankine cycle: boiler, turbine, condenser, pump. And if I said calculate the thermal efficiency of this cycle, you would say the thermal efficiency is output over input. Output is the work net, which is work turbine minus work pump, and divided by Q added. Okay, that's the thermal efficiency. So now in this chapter, he called the power, the work output, as P, and he called the Q added as F, right? So if I said this, we call this F and we will call this P. And I said, what is the thermal efficiency of this Rankine cycle? Output over input. So P over F. That is the thermal efficiency, right? Whatever we get and how much fuel we are paying. And this can be in BTU over PTU, or you want to turn this into CCF and CCF, or kilowatt hour or kilowatt hour. The point is output over input. But now when we have a combined heat and power production, so rather than just having output electric energy coming out, he will get some of the steam in this Rankine cycle and have heat exchanger, and he will get Q. Whatever his method to extract that energy, it's the gas turbine, and you get the power, and you get some Q in the exhaust, in the heat recovery boiler that will be sitting in the exhaust. The point is you have two output now, P and Q. Okay, and you are paying fuel in the boiler to generate this and generate this. So if I ask what's the efficiency, thermal efficiency of this power plant, you would say output over input, P plus Q over F. So that would make sense, but they don't do this. Okay, although this is kind of the thermal efficiency of the plant, we are building this to get those two guys, and we are paying for the natural gas we are burning over here. So rather than using this, they use the definition for Federal Energy Regulatory Commission combined efficiency. Okay, so the FERC efficiency. So what is FERC efficiency, eta FERC? Rather than saying P plus Q over F, they would say it is P plus Q over 2 over F. Why? Because they realize that joules in heat is not as equivalent in joules in electricity, right? This is like half as valuable, kind of. Why? Because in order to come up, or this is twice as expensive energy wise. Why? Because in order to come up with this power, you need to burn natural gas in a power plant, and that power plant will not have efficiency more than 50%, more or less. And so, I mean, you cannot just add them together. So you would say P plus Q over 2. That is the efficiency according to the FERC. Alright? So P plus Q over 2 over F. So now when you think there's another efficiency they define, which is the fuel utilization efficiency. Fuel utilization efficiency. So FUE or eta FU. So what is the fuel utilization efficiency? So we are spending the fuel to come up with P, right? P. So it will be P over F. It will be the kilowatt hour over the BTU. Kind of what? The heat rate. Remember the heat rate for a power plant? So it's how much kilowatt hour for BTU that we are spending in the inverse, right, of the heat rate. How much kilowatt hour for the BTU that we are spending in the boiler. But this is not all spent. There is not all of this is being used to calculate the power. There is a little bit of saving. And how much we are saving, that if some of it go into Q, by eta Q, whatever the efficiency of burning the fuel and efficiency of the exchanger, how much is getting lost of the wool. There is a heat transfer efficiency, and there is, so to turn fuel, to turn F to Q, there is eta Q. Okay, and so that amount that you are utilizing from this combined heat and power system is kind of saving on the natural gas that you are burning. Okay, and so it reduce the amount of fuel that would have been burned otherwise, because otherwise you would have burned that fuel to come up with the power, and you would have burned more fuel to come up with Q. So this is the definition of the fuel utilization efficiency. Alright, and finally, if we look to those two systems, what we have combined heat and power, where you get some power, you get some Q, and you pay F. That's the fuel you pay. And the alternative, what's the alternative? You get the power from a power plant, just doing electricity, and you get the Q from just like a furnace and a boiler. If you wanted that Q, you would have burned how much? Q over eta Q. And if you wanted that power, you would have burned natural gas equivalent to P over eta P. So this would be the total of natural gas that you would burn if you did everything separately. And this would be the F for our system. So then the saving fraction, what he called over here, the saving fractional energy saving, that fractional energy saving is how much did you save? You were supposed to burn this, but now you are burning only this. So you're supposed to burn P over eta P and Q over eta Q, the kilowatt hour coming from the electric generation, and the BTU that you are using for your process heating. This is what you're supposed to burn, but instead you are burning this. So the difference is the saving divided over what you were supposed to do. That would be the saving fraction. Okay, so just the mass, this guy over this become 1 minus this. So this is his definition for the fractional energy saving. And he have an example over here when he basically just calculate those three numbers again for you. He calculate so he tell you how much a power he need and how much Q he needs. And the only trick in this problem is energy conversion. The only trick is energy conversion. We need to turn everything to the same units: the fuel, the power, the Q. So what if he end up saying the fuel is in CCF and the Q in BTU and the power is in kilowatt hour? You turn everything to one unit. Okay, so CCF sounds like a great idea. So after he did the conversion, he turned everything to CCF. Then he can calculate the thermal efficiency based on the definition. He calculate the FERC efficiency, P plus Q over 2, and he can calculate the fuel utilization, and he can calculate the saving fraction. Those are all just a definition of how you can evaluate the system, but they have meaning too, right? So for example, that saving fraction, saying 0.3%, that means that you are saving 30% of the fuel by doing that combined and heat and power production. 30% of the fuel is not being burned right now. So one can remember the combustion calculation that we did last time. So if I tell you we are saving 30% by moving to that system, then you can calculate how much CO2 we are saving by switching to that system. And then if there is a CO2 tax credit or something, you will be able to calculate, so going to that system, how much dollars you will get for reducing the CO2 emission. Okay, so this makes sense. Those systems make sense energy wise, right? And of course for big power, big hotels and big hospital and big campus like universities, people should do this. But the question is, can we do this at our home? Can every one of us have his own small power plant sitting in the garage, in the closet, and basically you can get your power and you can get your heating, right? So the three things: we need to have the need for the power all the time, we need to have the need for the heat all the time, and the spark spread should be large, the difference between the electricity and the gas, natural gas. And so the Department of Energy realized that this is a great idea, and a few years ago they had this call for proposal, how we can design a very efficient CHP system for a household, a typical household in America. Okay, small scale cogeneration. So cogeneration, what does cogeneration mean? You are generating electricity and heat at the same place. So cogeneration does not mean combined cycle. It does not mean you have a gas turbine and the exhaust is turning it into another power by putting a Rankine cycle under it. No, cogeneration means you are doing combined heat and power system. Combined heat and power. So in order to have those small, there's a lot of paper that basically deal with small and micro CHP for small places, and here are example of the how large they will fit. So it's not really that big, and those system will, you can see here, they will generate basically power and electricity. But the one bad thing about those system is, what do you think? Free quiz. What is bad about having something like this? It's the efficiency. Those systems have small efficiency. All those systems have small efficiency compared to a steam power plant. So a steam power plant should hit 40% or higher, right? 40%, that's like a really bad steam power plant. A combined cycle steam power plant would be 60 something, right? But let's not talk about combined. Let's just like compare it to a regular steam power plant. So we should hit 40% efficiency, right? And the problem is that with small power unit, something that will fit in a household, 5 kilowatt, 10 kilowatt system, the efficiency are typically low, right? And that's what you guys will see in the project when you're trying to, in our project, when we are trying to see how can we run a house with a small generator, and you are trying to find a generator that we can buy from Lowe's or Home Depot, you'll find out that the efficiency is very small. Okay, so the Department of Energy was saying, well, this idea of combined heat and power cycle would be great if only we can match the efficiency of a steam power plant from those small units. Then it's double winning basically, right? Why double winning? Because you are using the Q. That steam power plant does not use the Q rejected. So all the heat going into the condenser just go wasted in the river. But if you do it in your house, you will be able to use that Q. So you move immediately from eta thermal to eta basically CHP, the eta of the combined heat and power system. So it will be Q plus the P divided by F, right? So you will consider the heat as part of your output. So theoretically speaking, if we do this in our home, the efficiency would be 100%. I mean, of course, the Q will not be, you will not recover all the Q, but theoretically speaking, you are above Carnot cycle now. So Carnot cycle, which said the efficiency is work over Q, now we are saying work over Q added. Now we are saying the efficiency would be the work plus Q rejected over Q added, and that is theoretically speaking 100%. But of course, the Q that we will absorb is not going to be all the Q rejected. It will be smaller fraction, right? 50% we said last part. But anyway, the efficiency will really increase, and you don't have to worry about power line coming to everywhere, right? So they try to do this, but again, that is the challenge. And you can see in the literature there's a lot of papers that are trying to improve the efficiency of small units for that purpose, for basic electric power generation, how we can make small units really very efficient so that we can utilize them as our main power a generation unit in distributed power generation. So that term distributed power generation is rather than one central power plant sitting and feeding the whole city, everyone has his own small power plant. Okay, so of course again efficiency is really hard, and that's why they have all those innovative design. So in that design, that's a free piston engine. There's no crankshaft, the piston is just going up and down, and there's electric generator over here, and he's using the exhaust to, so the compressor is doing the compression for the engine, and the exhaust is very hot, is basically used for the running the turbine, which is running the compressor, but you also get power stroke in that engine. So there are all this idea to improve the efficiency, and hopefully in the future we will see something like this in every one house.